Hello, everybody. Thank you very much. It's my great honor to attend IEEE Census 2020 virtual conference and have an opportunity to talk about my research. My paper title is Analysis and Experiment on the Parametrically Amplified and Push-Pull-Driven Resonators. Here are the authors, and I am Wu Kai from National University of Defense Technology, Changsha, China. My presentation is composed of these four aspects, and the first part is the research background. I'd like to take a brief introduction about the parametric excitation in previous study. Parametric excitation refers to a method of excitation whereby a resonance system may be set into oscillation by periodically varying one of the parameters of the homogeneous system. For MEMS resonators, the varied parameter was generally the stiffness. This figure shows the macro ring resonator in Gallicus study. The parametric excitation voltage VDT combined with the frequencies of omega f and double omega f was applied to the only one electrode of the 8, and all the other electrodes are held at earth potential. And this is the open loop parametric amplification in sense axis. The double omega parametric pump is also applied to only a single electrode of sense mode. These parametric excitations for symmetric gyros, as mentioned above, are all applied to a single electrode, which is less efficient. Therefore, we come up with the parametric excitation in push-pull driving method to improve efficiency. In this part, I'd like to talk about the theoretical analysis of parametric excitation in push-pull driving resonators. Generally, the disk resonator gyroscope, which has a symmetrical structure, is actuated by the push-pull driving force. Because this driving method is efficient and it can separate the asymmetry that caused by manufacturing errors. This figure elaborates the implementation of push-pull driving in disk resonators. The differential voltages Vd and minus Vd are applied to the two pairs of driving electrodes, and the DC bias voltage is applied to the anchor of ring structure for actuation and sensing. If one direction of the resonance structure is pulled, the vertical direction will be pushed. In this case, the energy of driving force can be fully utilized. When the parametric excitation voltage is applied to the push-pull driven resonators as what this figure does, the driving force will be given by this equation. As a consequence, the terms of F that related to the parametric amplification is symmetrically eliminated due to the differential method. And as what we can see, there are no double omega terms in this equation, thus no parametric amplification effect in this case. Therefore, we come up with two modified methods to enable parametric amplification in push-pull driving method. The first method is the triple frequency parametric excitation, as shown in this figure. where the frequency of parametric excitation signal is 3 times the resonant frequency instead of the traditional twice. Under the circumstances, omega p equal to 3 omega d, and only in this frequency. A coefficient of x containing twice the resonant frequency can be generated in the expression of driving force F as shown in this equation, which can be used to achieve parametric amplification. The related experiment also, such as 2, 4, and 5 times, have no parametric amplification effect, which also support this point. However, the efficiency of triple frequency excitation is not satisfied because that there is just a small component in the driving force and that can achieve amplification, and it depends on the magnitude of driving voltage Vd as what we can obtain in this equation. Therefore, we propose another method to increase efficiency. The second method is the non-differential parametric excitation method, that adding the same twice frequency signals to the driving electrodes without the differential transformation, as shown in this figure. Now the driving force is given by this equation. In this case, the effect of parametric amplification depends on the DC bias voltage VDC, which is much bigger than the driving voltage Vd. Therefore, a smaller parametric excitation voltage is required to reach the same effect of amplification as what triple frequency does, and its efficiency has improved sufficiently. Next is our experiment results. In this experiment, we keep the gyroscope vibrating at a certain response amplitude and compare the required magnitude of driving voltage Vd on the different parametric excitation modes. For the same vibration amplitude and parametric voltage Vp, the higher the efficiency of parametric amplification is, the smaller the driving voltage Vd is required. This figure is the driving voltage Vd and its decrease percentage varying with the parametric excitation voltage Vp. When the parametric excitation voltage of triple frequency increased from 0 to 3,200 millivolts, the driving voltage had been reduced nearly half as shown in figure A. While the non-differential twice frequency method, however, only 280 millivolts was required for a same 50% decline for driving voltage. The right figure shows the driving voltage and its decrease percentage varying with response amplitude. In this experiment, the gyro vibration is controlled at a stable amplitude by a PID controller, which increases by 50 millivolts from 50 millivolts to 1,100 millivolts in turn for each vibration amplitudes. The required driving voltage for different excitation modes are recorded. The slope of decreased percentage of driving voltage remains nearly the same level as shown in Figure B, which is much smaller than that of the triple frequency excitation shown in Figure A. This is because that the degree of driving force reduction is affected by both the DC bias and the driving voltage Vd, and the DC bias is much bigger than Vd. The decrease of Vd has a slight effect on its decrease percentage, but not a great one. The frequency sweeping was implemented in the drive mode. The driving voltage was maintained at 5 mV. When not parametrically amplified, the oscillation amplitude is merely 24 mV. The peak value is ever increasing with the increase of non-differential twice frequency voltage. When the parametric excitation voltage was 700 mV, the oscillation amplitude has reached about 550 mV, about 20 times the condition that not parametrically amplified. Finally, in conclusion, as mentioned above, both methods can achieve parametric amplification in push power-driven resonators. In this way, with the decreasing of the driving voltage, the coupling effect from drive mode to sense mode can be reduced, leading to the suppressing of signal crosstalk, which is of great significance to improve the performance. In addition, the non-differential parametric excitation method has been proved to have a higher potential for parametric amplification effect. This is the references. Okay, that's all what I want to say from now on. Thank you very much for your guidance, and if any questions, please contact with me. Thank you.